say or to propose for today? Okay. So, let's say, if you have any exercise to propose, anything to otherwise, okay, let's do this. There is actually one topic that I wanted to touch and that I skipped because I wanted to, well, approach the conclusion of the course. But actually, it's a topic that might help you understand some other topics of the course. In fact, a few weeks ago, we spoke about the singular value decomposition technique. And if you remember, it was a way to take any kind of matrix, any matrix, be it square, rectangular, or anything else, and write it as a product of three very special matrices. In fact, if you remember, U and V are have orthogonal columns, which means that they are actually rotation matrices. They change coordinates by maintaining all lengths and so on unchanged. So U and V are real coordinate transformation matrices. And this means that you are starting from some space A, and you go and do computations in another space inside here, where matrix A becomes diagonal and hopefully even smaller. In fact, if you look at how the element Aij is computed, what is the element Aij? It's the product of row I of U and column J of V transpose. So it is actually let's see, row U, so U I K, well, with the kth value of matrix sigma in the middle, and the element Kj of V transpose, so the element Jk of matrix V. And everything summed up on coordinate K. K, so is an index that varies from 1, of course, to, actually we have seen that here inside this transformation, what matters is the rank of matrix A. So the number of independent rows or columns, which we called R. Next, we also saw that if, as required in the SVD transformation, the values of sigma are sorted by their magnitude, then we can compute an approximation of Aij by cutting our summation, our sum, to the largest of these coordinates. So only taking r prime, where r prime can be even much smaller than r here. Okay. Now, here you see we have some symmetry in this formula. In fact, I mean, both u and v are orthogonal by columns. So, from the STD transform of A, we easily get the STD transform of a transpose, of course. There is another kind of symmetry that we can discuss. So, suppose that we create matrix U prime, which is simply the matrix, let me see, I have to multiply the columns, it comes after, okay. Let's write sigma power 1/2, a sort of square root of matrix sigma. You know that sigma is simply a diagonal matrix with values from sigma 1 to sigma r. And we also know that all sigma are greater or equal to 0. They are all non-negative. So actually, we can define matrix square root of sigma by taking simply the diagonal matrix with square root of sigma 1 up to square root of sigma r. So, if we define u prime like this, and for the same reason v prime as v square root of sigma, by this definition, we have that matrix A can be also written as u prime v prime transpose. Okay, just to get rid of everything that is in the middle. Now we have just two matrices, U and V. And let's see. Here we can also do the same. Well, just a moment. Here, okay, the original matrix U was orthogonal, actually orthonormal. It meant that all of its columns had a norm equal to 1. Okay, they were all unit vectors and orthogonal with to each other. While, so all columns had the same length when you saw them as vectors. Now, U prime is different because you are taking the columns of U and you are multiplying each column of U by a different number, and numbers that are decreasing. So you can expect the first column to have a high norm, and while you proceed column after column, the norm of the column is smaller and smaller. Okay, we we took the singular values and we put them directly in the columns of the matrix. So that now, in U prime, the first columns are important because they are large, possibly larger than 1 because sigma 1 can be any number. And moving from left to right, the columns are smaller and smaller. So, also in this case, exactly as we did with the original formulation of SVD, we can take an R prime approximation of U prime by removing all columns after column R prime. Okay, so like before, we can have an approximation of A by only taking the first R columns of U and the first R prime columns of no, it's here. Sorry, okay, the first R prime columns of U prime and the first R prime columns of D prime. Okay, this equation is exactly this one. I just took sigma k, split it into 2 square roots, and glued it to uik and bjk. It's like taking sigma k and writing sigma k 1/2 twice. One, it was put together with matrix U, and once it was put together with matrix V. So, what we get is an approximation of this kind. If this is matrix A, we took the matrix U prime of, I don't remember the names I used for rows and columns, but let's use the standard ones this time. We have M rows and N columns. Okay. So we get an approximation of A by having U prime with M rows and only R prime columns, and matrix B prime having R prime V prime transpose, well, with an R prime down here also. Okay? So they're not the original matrices because I cut off a few of the smallest columns and N columns here. We can also draw this in a different way. The idea is that matrix A is approximated by an N by R prime matrix, which we call the U prime approximation R prime, and an R prime by M matrix that we call the V prime R prime, So that the generic element Aij is approximated by multiplying this row, the I row of V prime R prime, by the jth column of V prime R prime transpose. So, apart from the many symbols and many prime signs that I put here, the thing that should be clear is this. I took the original singular value decomposition of the matrix. I just got rid of sigma by splitting it into two square roots and gluing them to U and to V transpose, where they act as column multipliers. If you take U and multiply it by a diagonal matrix on the right, you are actually multiplying its columns. For the same reason, here I'm taking a diagonal matrix and multiplying it on the left on V transpose, so it acts on the rows, meaning that it acts on the columns of V. Okay, both U and V are column multiplied by sigma. Now, the second thing that I did was, okay, don't use all the R columns of the matrices, but just reduce to the first, most significant R prime columns. And what you get is something like this, where an element of Aij is the product of these two parts, meaning it is the dot product of one row of U and one row of V. One column of V transpose meaning one row of V. Okay, from this drawing, it should be clear that if, let's give some practical interpretation of this matrix. For example, this matrix, we have seen it in the context of documents and terms. This formulation is usually employed in recommender systems. So let's say that these are customers, let's say users, and these are items, and the element Aij is actually the preference that user I has for item J. Meaning, for example, that this is a movie rating system, a bookseller, or something like that. And this gives a measure of how user I likes, how much user I likes item J. Okay, is the recommender system setting clear to everybody? There should be no particular problem. Okay, so if you look at it this way, the matrices that I call the U prime R prime and V prime R prime are actually strictly related, well, this to users and this to items. So, in a sense, every row of matrix U prime R prime actually, represents one user. Every row of V prime R prime represents one item. The preference of a user for an item is given by the dot product of the two rows. So we could simply rename the two matrices. For example, I could call them okay, users would be U, but U was already taken there. Let's call it okay, this is C for customers, and this other will be P for products. Okay, I don't want to use I for item because I is also the name of the identity matrix, of course. Okay, so let's rename C U prime R prime, and P is D prime R prime. This is, of course, a real-valued matrix with, let's see, n rows and R prime columns, and V prime R prime, so P is a real matrix with m rows and R prime columns, where we have n users, customers, and m items. Products. Okay, so in this context, actually there are many different ways of, well, okay, let's stick to this notation. In this context, the element Aij is simply approximated by the sum for all R prime columns of, let's call it C ik P jk. Okay. You see, this this is fine. This means that we can, by using the singular value decomposition, we can actually obtain a matrices whose rows are characterizations of users and of items, in the sense that we already discussed, meaning that every element, so every column of this matrix can be interpreted as a sort of, it has a semantic sense. Okay, it means something. In the document term setting, the column here was, for example, something related to the topic of the document. Okay. In fact, when you speak of documents and terms, the elements of the matrix usually represent somehow the frequency of the term within a document. And these matrices represent a sort of rotation in the document and term space, so that one coordinate, instead of coinciding precisely with one term, would coincide with a linear combination of terms, which we could identify as a topic. The topic corresponds to some linear combination of terms. So the meaning of each column of this matrix is actually a sort of linear combination of the characteristics that are encoded in matrix A. And in fact, we saw that because of the ordering of the sorting of the singular values, the first column actually represents the combination of terms that is most significant in order to characterize the documents. This is also true for users and items. You only need to change context. So maybe okay. So these columns have actually some meaning, although it's not directly apparent to us. This is why we call this kind of decomposition, this kind of matrix analysis, we call it latent semantic analysis. Okay, latent means hidden. We look for some semantics that are not apparent in the original matrix. Okay, actually, we were left with one problem here. The problem is that to do these calculations and to end up with this, we actually need to determine matrices U, sigma, and Z, which is not always easy. They are not even guaranteed to be unique. But, okay, the main problem is this. Actually, if this is a recommender system, we have an additional problem with respect to the term document matrix, meaning that not all entries are known. In this context, maybe a user never saw this product. What's going to be inside this entry of the matrix? You see, there are cases where a user never rated an item. Maybe he never looked at it. Think of Amazon with users and books. Okay, not all users have looked at all books in Amazon. It would be impossible. So this matrix in the recommender system case is full of question marks, meaning we don't know what goes in this cell of the matrix, which is something that does not happen, for example, in the document term matrix. When you look at documents and terms, you can say for every term if it appears in the document or not, and how many times it appears. So usually the document term matrix in a document retrieval, in a search engine, is a complete matrix. Here, if we are working on a recommender system, it can happen that some entries are unknown. Of course, if entries are unknown, we cannot hope to use analytical means to compute this. matrices. Or we can use analytical means, but we need to slightly redefine the problem. So, the idea is this. We got to this formula that given matrices C and P approximates the element Aij. But of course, why does it approximate it? Just because I truncated them to R prime columns. If here I put R, then this is an equal sign. If C and P are computed by SVD. But of course, I can say this only if Aij is defined. So, what I want to do now is forget about the SVD decomposition. I want to get to something similar to latent semantic analysis of the matrix. But all I want to do is, okay, given matrix A, which is a matrix with okay, so n rows and n columns. Which is not true. Okay, I mean, if I write this, I mean that every entry in A, every cell of A contains a real number. So I'm implicitly saying that the matrix is complete. I know all numbers that appear in the matrix. Actually, what I want to say is that some entries, well, actually, in many real-world cases, most entries of the matrix are unknown. So maybe I can I don't want to be too formal because you need to introduce too many symbols, and I always have problems with symbols. I never find enough of them. But let's say that I define everything in something which we call R tilde, which is R plus a symbol that indicates unknown. So A is actually a matrix in this new space. Of course, when you if you write a program, a computer program with this, and you need to encode the matrix A, you will probably use a specific real number to encode unknown, or depending if your language accepts it or not. Suppose that you have a not a number value added to R. So the current floating point implementations all allow for infinity and for not a number symbols. So consider that this matrix is full of question marks. Your problem is this. Given this matrix, and given some value of R prime, which, for the sake of computation, we assume that is much smaller both of n and of m. Given the matrix, given R prime, compute these matrices C and P so that this approximation holds. Okay, this is our problem for today. So the problem is a consequence of the singular value decomposition, as I hope I have shown you earlier, but we don't want to use analytical means to solve it. Okay, the problem is that we need to define more precisely what we mean by approximation. So, when are we happy with C and P? When do we say that these two matrices approximate the known values of A? Well, the idea can be this. Okay, suppose that Aij is in the matrix is known, so it's not a number. It's a number. Okay, let's write it. Suppose that Aij is a real number. It is known. Let's call A prime ij the approximation computed by that formula. From 1 to a prime of Cik of P jk. There will be a difference between the two, between the actual value, the actual preference of the user I for item j, and the preference that we computed by multiplying the vector related to user I and the vector related to item j. Let's call E ij the difference between the two. This is the error that we make in estimating the actual user preference by our model. Okay? Remember, what we are building here is actually a model of the users. We are representing users in an R prime dimensional vector space. Every user is a vector with R prime numbers, and we are modeling items. And here we build a model of the user preference for an item. And this is the error that we make by estimating the actual value of the preference by the model that we have built. Okay, this is one of the errors. What we can do is actually try to minimize the average error. Of course, positive or negative errors should have exactly the same influence on the overall error. So what we really want to compute is, let's say, the sum along all I and j such that aij is a real number, okay, by only considering the actual preference values that we know and excluding all the question marks in the matrix. We compute Eij squared so we sum the squares of the errors so that the sign does not matter anymore. Of course, we divide by the total number of elements in the sum so that we get an average. So it's the number of aij, so that so the number of indices I and j, so that aij is a real number. And the square root of this is what we call the root mean square error of our system. Okay, we take the arithmetic mean of the squares and then we take the square root. This represents a sort of the average error that we can expect to make when we compute a user preference using our model. So actually what we want to compute are all the numbers in C and P, so the values of the matrices C and P, so that this root mean square error is minimized. So the best formulation that we can give about the problem is compute C and P so that this is minimized. Okay. Any questions? Okay. Okay, the problem now is we want to minimize this. Actually, okay, so if we want to minimize this, well, actually we only need to minimize the sum of the squares. Okay, everything else is constant. The fact that we divide by this number, which is always the same, or the fact that we take the square root, that of course is a non-decreasing function, an always increasing function of positive numbers, doesn't change anything. What matters is that we minimize this sum of squares. this is actually what we want to minimize. Okay, the problem now is, how do we minimize that? Okay, let me erase this part. Let's write explicitly what I want to minimize. So I have this sum for all known values in the preference matrix, and here I want to sum the square of the error. Square of the error is the difference between the original value v and j and the sum along k of c I k minus times p j k, and this is square. Okay, this is what I want to minimize. Actually, this is the simplest problem that we want to minimize. Actually, sometimes we should also make some more approximations to make things work better. Okay. Actually, you see here, we are just working with, we need to determine these real numbers. Okay. How many? N times r prime plus m times r prime numbers. This is a quadratic problem. No, actually not, because we have a square of product. So, it's not really a quadratic problem. This problem, so we want to minimize this. Okay, this problem can be solved by, for example, by a gradient descent method. Let's make a small analytical digression here. Suppose that you have a function f from a generic n-dimensional real space to the reals, and you want to find a minimum of the function f. Let's look at the simplest case, n equal to 1. One way to find the minimum of a function, well, how do you characterize a minimum of a function, for example, from R to R? Well, minima are, like all other so-called stationary points, are points where the derivative is 0. Okay, first course of calculus. So for sure, if you want to minimize this function, you need to find a place where f prime of x, let's call it star your solution, is 0. Of course, there are many places where the derivative of a function is usually 0, can be 0, but if you have no constraints, borders, if you can extend on all R, then and the function is continuous, there are many things that you have to say about the function. But let's say okay, let's suppose that the function is continuous and everywhere differentiable. It's easy to conclude that this is the case. Okay, this is for sure continuous and differentiable. Suppose that you are looking for this value x star where the derivative is 0. One way to be sure that you converge to a minimum is start from, suppose that you cannot solve analytically this. What you can do is start from from a random point x. At that point, you look at the direction where the function decreases, meaning that if, in this case, for example, here in x, the derivative is negative, it means that the function is decreasing if you increase x. So you can just look at the derivative and move x in the direction where the derivative decreases. If you do it by sufficiently small steps, and you allow, of course, for some error in the final result, you can actually converge to an actual minimum. Of course, depending on your starting point, you will fall down this slope down to this x star here, but maybe also, if you started from here, fall down to a different local minimum, which is not the global one. Anyway, imagining that you see this is an actual slope and this is and you place some ball here, in order to find the lowest position, you just need to let the ball free to roll down the slope. The ball will end in the minimum of the function. This also happens in more than one dimension. It's simply more difficult to describe, to draw it. One possibility is this. Suppose that n is equal to 2. So you have a real valued function of 2 variables. Well, in this case you can use a geographical metaphor. You can imagine that you're looking at the graph of f from above, so that this is a sort of a map of function f, and you can draw the lines of equal value of f. So if this is x1 and this is x2, So the function in this point will have the value f of x1 and x2. It's a function of two variables. Then you can draw the locus of all points at x1, x2 where f has the same value. On a geographic map, this means the locus of all points that have the same quota, the same height. If you take any map for hiking in the mountains, for example, you find these lines so that you easily identify the top of a mountain or bottom of a valley. I actually don't know the name of these lines in English. Actually, I'm not sure I know it also in Italian. Anyway, I hope you understand what I mean. Yes, contour lines, sometimes, okay. Okay, suppose that the function is decreasing. For example, this is the bottom of a valley. Okay, there is some gentle slopes that go down from all directions. You start from, suppose that you are actually hiking, you walk around, and you want to reach the bottom of the valley. What should you do? You should just always walk down. If you walk down, you are guaranteed that you will end up on local minimum, so on a place where you can't go possibly lower. Well, it depends, of course, but at least in this case. Okay, how do you identify the direction of fastest decrease of your quota? Well, if this is the contour line that represents the points of equal quota, then you just need to go perpendicularly with respect to that line. And it turns out that the perpendicular direction is given by the gradient of the function at this point. Just a moment. So I already called x1 and x2 this, so this direction is the gradient of the function computed in x1, x2. What is the gradient of a function? Is the vector of the partial derivatives of function f, computed in the given point. So actually, to find the minimum, you need to sorry, I'm going down, so this is minus the gradient, actually. Okay, in order to go down as fast as possible, you just need to compute the partial derivatives of the function, and, well, if you want to minimize, you go against them. So to minimize this, I only need to compute all partial derivatives with respect to the variables that that I can change, that in this case are Cik and Pjk. And this gives me the direction that I need to use to modify the values of these variables. So, I just need to take these derivatives So for example, the derivative with respect to Cik of this sum okay, how do I compute it? Any idea? Well, actually, it's not that difficult because this is a derivative of a sum, so it's equal to the sum of derivatives. Second, so write this as the sum for I and j of the partial derivative with respect to Cik of Aij minus sum over k of Cik Tjk squared. But actually, many of these do not contain Cik. The only elements here that contain Cik are the ones where, as usual, I'm using too many indexes. Just a moment. Here I'm using I with a meaning here and with a different meaning here. So let me put some prime signs along here. Also k, I, k, j prime, k prime. The idea is that only the parts where I prime is equal to I have a derivative different from 0. So this sum just becomes a sum over j prime such that Aij prime is actually a real number of the derivative with respect to Cik of Ai prime j prime, but with I equal to I prime, so Aij prime minus the sum over all k primes of Cik k prime p j prime k prime squared. Okay, I only took the elements in the sum where I is equal to I prime. So here we get the sum over j prime such that and so on. This, the derivative of this is simply twice Aij prime minus sum over k prime of Cik prime p j prime k prime times the derivative of the interior of the square. The derivative of the interior of the square, here it's 0 because this does not depend on CIK. The only element here that depends on CIK is for k equal to k prime. So it's times minus p j prime k. So this derivative is, if I write it a little better, 2 sum over j prime, so it's minus 2 p j prime k times a I j primes minus sum over k prime of ci k prime p j prime k prime. Okay, so this is the derivative of the error with respect to one of the elements of the two matrices that we want to compute. Unless I have made some errors, of course. For the same reason, the derivative with respect to one element of the item matrix Pjk of the same sum I prime j prime of a I prime j prime minus sum of c I prime k prime p j prime k prime square. This is, for the same reason, minus 2 sum over I prime of c I prime k times a I prime j minus sum over k prime of c I prime k prime p j k prime. So we have all the partial derivatives of the function that we want to minimize with respect both to elements in C and to elements of P. And those derivatives are all that we need to try to minimize our function. To do it, we just need to start. Let's write a short pseudocode of what we need to do. Let's say for all I in 1n and for all k in 1 a prime, we set a random value for CLK. For example, a random value in minus 1, 1. For the same reason, j and 1, m, and for same set of k indices, p, j, k takes a random value in minus 1, 1. So let's start by putting random numbers both in the user and in the item model. Of course, this will give a completely random result in when you try to compute the matrix A, but then we can repeat the following. In turn, we take every element of C, Cik, and we move it against the direction of the gradient. So we need to take the previous value and subtract some small multiplier eta times the value that we computed for its partial derivative. So minus eta times what we computed as the partial derivative of that sum, or let's write it minus 2 sum on j prime of pj prime k a I j prime minus sum and the same for all p jk's. Pjk minus eta times the derivative that we computed here. So what we are doing is we start from a random model, but then we constantly move our point against minus the gradient in order to go towards a minimum of the function. By doing this, we should finally get, after a few iterations, to some combination of Cik and Pjk values that minimizes the error, the overall error. Of course, this is very simplistic. We should make many other considerations before being able of finding an actual value. We can actually, by doing this, as you saw before, we might not end up in the global minimum, but we could simply find some local minimum of our function. So we are not guaranteed that we are really converging to something that is the smallest error, the smallest possible error. The second problem is that we should add some constraints on the size of Cik, and of Pik in order to not let them grow too much. Those of you who have followed the machine learning course should be aware of problems such as overfitting. I mean, when you let a system work too hard in order to optimize some specific problem. I'm not going too deep in that. On this topic. So probably if we try something like this, we already get something that models our users and our items in a way that we can somehow predict the user's preference for an item. Well, let me only make some changes to the original formulation so that it becomes more well, it gives better results. Okay, the idea is the following. Rather than starting directly with this user and item model, we can make a much simpler model and start from it. For example, we know some AIJs, some of the AIJs. We don't know all of them. We can compute an average value of all the known AIJs by simply computing the arithmetic means. So for all IJs such that AIJ is known, is a real number, we can add them up and divide by, of course, the same. So that AJ is real. Okay. If you look at these as, I don't know, the star ratings of a movie recommender system or of a book recommender system, this is the average vote that users have given to items. So if the votes are from 1 to 5, which is often the case, the user is asked to give from 1 to 5 stars to an item. So he actually gives a vote from 1 to 5. You can compute the average of all votes in the system and get an average vote. Okay. Second, so instead of considering the votes in your computation, you can consider the difference between the vote and the average. So what you use in the following is A prime ij, which is the difference between the actual vote and the overall average. The advantage of considering this is that it's centered around 0. A prime ij is equal to 0 when the vote is precisely the average. It's above 0 if the vote is above average, and it's below 0 if the vote is below average. Okay, so the first thing you can do is normalize your votes with respect to the average, to the arithmetic mean. Normalize things, so putting things around 0 is usually an advantage when you have to work with numbers and with models. You want that everything is placed around 0. If everything is positive, you tend to add some bias when you compute things. So, first thing you can do is this. Second, well, not all users are equal. I mean, of course, different users may have different preferences. This is obvious. But the problem is that some users are more difficult than others. Some users will tend to give low marks to things, while some users are more optimistic, or they like many more things. They tend to give higher ranking. So, if you take user I, you can compute the bias of user I, let's call it BI, as the arithmetic mean of his votes, of his normalized votes. So we sum all A prime ij and here we can sorry? Here we are only adding on j. So, but of course, on all j's such that aij is real. And divide, of course, by the number of j's such that aij is real. This is called the bias of user I. So, if BI is positive, it means that user I tends to give better votes than the average user. So he is he tends to like the items more with respect to the average user. If BI is negative, it means that the user is more difficult. It's harder to make him happy. So, you see, we could already have an approximation of the user's preferences by, well, not yet. We could compute exactly the same bias for item j. So, okay, I used B as the bias for the user. C is already taken. Let's say D. Okay, D is the bias of item j. Pj is, okay, exactly the same thing. This time we add over I, so that aij is real, of A prime ij. So we take the average. So here the idea is that if item j, for a given item j, the j is positive, it means that that item tends to be liked by many users. Its average mark is above the overall average. And the idea is that a very raw, crude approximation of a vote can be given by the overall mean corrected by the two biases. Okay, we can consider a series of approximations. Of course, the simplest approximation of all is, okay, let's approximate a vote by the overall mean. Okay. The purpose of a mean value is exactly that of approximating your data set. It's the value the single value that best approximates your data set. So this, we can call it the zero order approximation. Tries to approximate the user preference by systematically replacing them with the overall average. Of course, it's completely useless because you give the same value to all users and items, but in some sense, among all numbers, mu is the number that minimizes the error of this particular model. This is the order 1 approximation. In order to predict the vote of a user for an item, you start from the average, from the overall average, but then you look at the user's bias. If the user tends to give higher votes, then BI will be positive and will add something to the average vote, and you look at the item bias. So you are adjusting the vote depending separately on the users and on the items characteristics. What's missing here is, well, what we actually need. Well, the important information that is missing here is interaction between users and items, which is exactly what we have done before when speaking of SVD. So, when we approximate AIJ in the way that we have seen before, so AIJ becomes well, we can write it like this: mu plus BI plus BJ plus the sum over k from 1 to r prime of c I k p j k see, this is, well, more or less exactly the same formulation that I gave before, but instead of using this to directly approximate the user's vote, I use it as a correction term with respect to the order 1 approximation. This part of the approximation is usually called the baseline. The raw approximation without interaction between users and items. This is the part that concerns that that takes advantage of the user model and the item model. Okay, so the formulation that is used for the problem takes into account this baseline, so that these factors only become a correction of a much simpler model that takes into account see, the idea is that the rough approximation lies here. If the average vote is 2.5, user I tends to give, on the average, half a vote more with respect to the average. Item J tends to receive lower votes with respect to the average of about 1 vote less than the average. Okay. This already gives us an approximation which is, okay, the vote that is predicted for item J by user I is 2 by this order 1 approximation. Next, we use this dot product between user I's vector and item J's vector to modify this vote, to add a small correction to this vote. So what we actually minimize is the sum for all I, j, so that Aij is real of the original vote Aij, the recorded vote by user I for item j, minus this approximation, so minus mu minus di minus dj minus the sum of, for k going from 1 to r prime, of c I k p j k squared. Okay, so the sum of the squared errors as before. We should add actually another term, because for reasons that cannot explain in 5 minutes. The idea is that we don't want the values of C and P to grow too much. This term should account for a small correction. So that, rather than minimizing only this sum of squares, we also add, as a minimization part, the sum here we have lots of indices as usual. Okay, the sum on all, we can sum k's here and i's here, say by k squared, plus sum on j of p jk squared. Okay, something like this. So the idea is that we take a small number lambda, but we add this term, which is the sum of all squares of all the variables that we are going to determine, in order to keep them small. This is a rather technical issue, but maybe tomorrow in the laboratory we'll see something about this. So the idea is that in a real setting, this is what we are actually willing to minimize in order to find a working model for our users and items.
And in the order 1 approximation, we approximate Aij with mu plus etc. And in the before, we have approximated it with the sum to R prime dCik.
Yes.
So when we approximate Aij with the sum of 1 plus the others, isn't it 2 times the Ij? 2 times in the center equation.
Means that the correction is Ij per se. The correction part is Iij, and the first part is Iij.
No, just a moment. Yes. No, I mean, instead of determining C and P as before, we determine them in order to get this approximation, okay? The meaning of C and P here changes. Sorry, probably I wasn't clear enough here. Okay, they are not the same C and P as before. Okay. Earlier we used them to determine A completely. Now we use the same formulation, but only for the correction part. So they are not the same C and P as before. But using them this way should yield better results, because now we are using them to compute something that is hopefully centered around 0, which is rather important when we compute dot products of vectors, which can be both positive and negative. And they should be small, because most of the magnitude of numbers should be on this side. So this part should hopefully be a small correction, which is better since we are using many numbers. Okay, anyway, maybe tomorrow we can write something to experiment with this and see how the different approximations yield different different values, different results. Okay. So for today it's all. We see you tomorrow for the last lesson.